Okay, today we are going to do 5.1a, which is the very basics of verifying trigonometric identities. So this is kind of different math than you've ever seen before. And the key here is it's kind of like a puzzle. You have to figure out how to get one side to look like the other side. Before we get into that, I want to just go over a few important details that you cannot miss. So important, I put them on neon paper. So the first one is, we are not solving an equation when we are told to verify trig identities. You have to manipulate one side of the equation independently of the other. So you can't use the phrase that we use when we're solving equations, which is what you do to one side, you do to the other. No, you work one side and you work the other. So you don't multiply both sides by 2, you don't divide both sides by the sine of x. You can't work both sides at the same time. Okay, next important thing is when you're doing these, proper protocol is to write both sides of the identity throughout each step in the problem. So you might have to watch some YouTube videos, and maybe another teacher doesn't have as high expectations of her students, but I do have high expectations of you, and I want you to do things properly. So in math, we write these identities on both sides, so we don't get lazy and just write one side and add it in the end. That shouldn't be a surprise to you that I have that expectation. Also, something that we typically do, which means not always, but you can have your choice, is we work one side only. Sometimes we're not figuring this out by working one side, so we switch to the other side, and that's fine. It's not incorrect. But when you see me working these problems, it's because standard procedure in math is to typically work just one side. Like I said, you can work both sides as long as they are worked independently. So again, that what you do to one side, you cannot do to the other, because you shouldn't be touching both sides in the same step. Okay, next. Oh my goodness, look at this. This is so much. Okay, this doesn't really make that much sense to you till we get into these examples, but we need to be aware of them. So the first thing is everybody is going to get out their trig functions sheet for me. So you get to use this sheet of paper on your test and on your quiz. So you do not have to have these equations memorized. So this is the one that you're picking up. You got it when you walked in, and you have all these identities. So today we are going to be using the Pythagorean identities, the quotient identities, and the reciprocal identities. So again, in today's homework, those are the 3 identities that we're practicing, how to use those, what they look like. So the first thing that I have here is when we are trying to show that one side equals the other, we are going to put it in terms of sine and cosine. That means that we can use the quotient identities. So this is one you should be familiar with, meaning it's so much easier for you when you're working through problems if you have this memorized rather than having to go to the sheet every single time. So the tangent of x equals sine of x over cosine x. That's this one right here. And then the cotangent of x is clearly the reciprocal of that, since tangent and cotangent are reciprocals of each other. I did use different variables. These problems will switch variables as long as the angle is consistent. So are the trigonometric identities. Here's another one, secant x. It's a reciprocal identity. We've been using these all along. 1 divided by cosine is the secant reciprocal. So yes, you can rewrite cosine x as 1 over secant x, but when we're working these problems, we generally try and change things to sines and cosines. So even though you can go the other way, usually the problem doesn't require it. So these are pretty much the 4 that you want to be familiar with that. Another trick that you can try is to get common denominators. So let's say I was asked to do this expression right here. So when you're doing something like this, you might think, what the heck, we can get common denominators with trig functions? Yes, we can. And how do we do it? The exact same way we do it with regular numbers. So this one needs a sine theta. What I give to the denominator, I give to the numerator. So that's here. And this one needs a cosine theta. Same thing here. So over here, this would look like sine squared theta plus cosine squared theta over sine theta cosine theta. We're going to learn a new trick about this one right here in a couple minutes, but for now you can see how we get common denominators, the same way we get them in every other problem. Another trick is, let's say you actually have one fraction instead of starting with 2 and going down to 1. What if you have one fraction? You can split it into 2. It's the reverse of common denominators. Why would you want to do this? Well, it only works when you have one term in the denominator. So again, let me say that. It only works when you have one term in the denominator. And I'm going to take this and write it as a fraction. And I'm going to take this and write it as a fraction. So, like it says, reverse common denominators. Why would that be an advantage for us? Well, look at this. What will this fraction reduce to? This would be 1. And then here, sine over cosine would be tangent alpha. That's from one of the ones we have right here. And then sine beta over cosine beta would be tangent beta. So there's a new way to write that, which might be helpful for us if we're verifying identity. Next, just like you can get common denominators with these things, you can also factor. And do you see this is a perfect square and this is a perfect square? So guess what? Because we're subtracting two perfect squares, we can use difference of squares. Just like we did when we have x squared minus 4 and it was x plus 2x minus 2. This one is the one that sometimes students don't catch right here. So look at that, cosine x minus cosine x times sine squared x. What do these have in common? This is a two-term problem and each of the terms has a cosine x. So I can factor out the cosine x, which just leaves this first term as 1 and this one is sine squared x. Okay? Another trick to try is to use the Pythagorean identities. So I want you guys to have this sheet handy as I'm working through the problems. Like 9 times out of 10, if you don't know what I did in a step, it's because I used an identity and you're not as comfortable with that as common denominators in factoring. But the most commonly used identities are these Pythagorean identities, and anytime you see a square, it might not always work out for you, but anytime you see it, your gut should be, okay, I'm going to go check these Pythagorean identities. So we have the 3 Pythagorean identities written on here, but you'll notice right here this says sine squared x plus cosine squared x equals 1, which is the first one. But right here it says or 1 minus sine squared x equals cosine squared x. You're looking at your paper and you're like, what the heck? I don't see that one. That's because these identities come in 3 different forms, and one of the only things you're allowed to write on your paper other than your name is this right here. So we're going to make life easy for you. And what if we solved this identity for sine squared x? So it would be sine squared x equals, now how would I get this cosine squared x to the other side? I would subtract, so I get 1 minus cosine squared x. Okay, what if I solved it for cosine squared x instead of that? Well, here's cosine squared x. It's positive. How do I get rid of the sine squared x? I subtract it from both sides. We are not verifying, which is why we can do this. This right here, we're just simply rewriting it in terms of another variable or another trig ratio. So right here, what if I wanted to solve this one for tangent squared? It would be tangent squared x, and over here it says plus 1, so another version of this would be secant squared x minus 1. And then furthermore, another version is what if I wanted it to equal 1? Well, there's a 1 right there, so what would I do? I'd have to subtract, so it would be secant squared x minus tangent squared x equals 1. Finally, we do that with this trig ratio as well. So we are going to have cotangent squared x equals cosecant squared x minus 1. And then we are also going to have cosecant squared x minus cotangent squared x equals 1 as well. Okay, so anytime you see a square, there's actually 9 Pythagorean identities. These are the main 3 that are used, but these right here can all be used because they're just versions of the same identity. Okay, I believe we have one more trick to try. So the last trick to try is to multiply by the conjugate. So multiplying by the conjugate, let's say I had this fraction right here, 1 plus sine theta. The conjugate is 1 minus sine theta. So then I get 1 minus sine theta, and I'm going to multiply, and then I get 1 minus sine theta over 1 minus sine squared theta. So that's multiplying by the conjugate. The very last trick to try is to, not actually a trick, it's just an FYI. The FYI is that whenever you have sine squared x, really this is just the lazy mathematician's way of saying sine x times sine x, but they couldn't write it sine x times sine x like this, because that shows that the x is squared, not the entire trig function. So we have sine squared x is actually the same thing as sine x times sine x, and samesies for the other trig functions. And samesies is the technical term I'm using for tangent squared x. That also means tangent x times tangent x. Again, mathematicians didn't want to have to write these parentheses every single time, so they were like, well, what if we just put it right next to the sign so we don't have to do that? All that, and now we are finally ready to start our lesson. So, have your trig sheet out, don't put that away, you don't need a calculator, and we are going to start with this right here. So everything I just talked about is all right here. The Pythagorean identity that we use the most is going to be sine squared x plus cosine squared x equals 1. So you're going to want to have your your goggles on to find that. That's weird to say, but that's what you're going to need. So let's go ahead and get started. So, example 1 says rewrite the following trigonometric expressions in terms of sine and or cosine and completely simplify. So, example 2 tells you to verify, but this does not. So, it just wants you to simplify. So, we're going to go through our list of tricks to try and see if we can simplify this a little. So, sine of theta is already in terms of sine or cosine. I sometimes have students who insist on changing it here, but that is not one of our tricks. Don't change sine to 1 over cosecant unless you can't think of anything else to do. So this is 1 over sine theta minus cosine theta over sine theta times cosine theta. So where did the sine theta, cosine theta come from? Well, this is tangent theta, and one of our tricks, our very first one of our quotient identities is sine x over cosine x. Why am I choosing to rewrite tangent? Because it says one trick to try to simplify these is to put in terms of sine and cosine. So now what I'm going to do is I'm going to distribute this to each fraction. And what you'll want to notice is because this is really cosine over 1, before you distribute, that fraction can reduce. So I get sine theta over sine theta minus sine squared theta. Where did the sine squared theta come from? Because sine theta times that sine theta. Well, this simplifies to 1 minus sine squared theta. Why is it 1? Sine divided by sine is 1. And then you might think you're pretty close to being finished, but my trick is anytime you see the sine squared, you should check a Pythagorean identity. So over here on our Pythagorean identity, we are going to be looking for something that says 1 minus sine squared x. What's another way to write that entire thing? 1 minus sine squared x can be written as cosine squared x. So this whole entire thing can be simplified to cosine squared. And because our angle is theta, we're going to use theta and not x. And yes, you need to use whatever angle is given in the problem. So for this one right here, when we're looking at it, we're going to try and simplify it. So we definitely could start by trying to switch this to 1 over cosine squared theta and this to sine squared theta over cosine squared theta. But because it's squared, I'm just going to check a trig identity first. So I'm checking my trig identities. Here secant squared x minus tangent squared x. Rather than going through and switching it to sines and cosines, I can just switch it to what? 1. Isn't that crazy? All of that equals 1. So this is 1 over, and then we have cosecant x. And what is 1 divided by the cosecant of x? That would be the sine of x. So we got this one to reduce to cosine squared theta, and this one to reduce to sine of x. So these are the kinds of problems that you will be getting on your quizzes and tests most likely on the multiple choice portion. From example 2 on, there's no correct answer. You already have the answer, right? This side needs to equal this side, and so we're going to make this a little puzzle game of how to get the left side, or the more complicated side. We're going to try and get that to simplify to this. So there's another trick that we didn't write down, but try and work the more complicated side first. So this would be the more complicated side. So what we're going to do first with this one is step 1. I'm going to write the steps in a second, but first thing I'm going to do is switch everything to sines and cosines and see if that helps me in my simplifying. So this is actually cotangent, not tangent, so this is going to be cosine x over sine of x plus the sine of x equals cosecant x. So what happens here is a lot of times students want to try and get common denominators, but when you're multiplying fractions, no big problem, top times top over bottom times bottom. You don't need common denominators when you're multiplying fractions. So getting a little ahead of myself when doing that, I'm going to go back to where I wrote a number 1. You don't have to have these steps down, but this is where I'm putting everything in terms of sine and cosine. And then in step 2, to go from this step to this step, I'm just using algebra. Just using arithmetic, algebra, to go cosine x times cosine x is cosine squared x. Now it would be something, well, how many fractions do I have? I actually have 2 fractions, so that, since I am starting with 2, I could get common denominators. So what do I need? This one needs a sine x, and so does this one. So step 3, I got common denominators. So with that, we have cosine squared x plus sine x times sine x is sine squared x all over that common denominator of sine of x. And we're trying to get it to look like cosecant x. We see something that's squared. Again, this is the one that you're just going to know and learn to love because it's used so often, and when we see it, we like it because it's just simplifying to 1. So it doesn't matter in math the order in which you add. Cosine squared x plus sine squared x is the same thing as sine squared x plus cosine squared x. So this is 1 over the sine of x. And we know that 1 over the sine of x is cosecant x. So then our very last step is to say cosecant x equals cosecant x. So here in step 4, we used a Pythagorean identity. Now what I do want to say and point out, because I made it a big deal when I said, when I put it on the neon paper, notice how every single step it says equals cosecant x. On a problem where it says cosecant x, it's not going to bother you, but as these get a little bit more involved, you still have to do it. It's just proper math protocol. So I wouldn't want to send you to college and have you using bad form, like writing cos in your English papers. This is like that equivalent in math. Okay. So the next thing we're going to do, we're just going to practice today over and over again how to do these problems so that when you go to do your homework you have a good skill base. So this one right here, Put in terms of sine and cosine doesn't really make sense because why? They're already sines and cosines. Getting common denominators, I actually don't have any fractions, so that doesn't seem like a good trick to try. Split a single fraction into two fractions. These aren't even fractions I can split up. Oh, step 4, number trick to try 4, factor. So look at these and see, do these have something in common? Oh yeah, they both have a sine of x. So I take the sine of x out, and I get 1 minus cosine squared x equals sine cubed x, which remember, that means sine of x times sine of x times sine of x. Okay, I'm going to pause right here and just give you a little bit of algebra version of factoring. If you had something like 3x minus 9x squared, and I asked you to factor that, the way you would do it is say, okay, they both have a 3 in common because they're both divisible by 3, and they both have an x in common, so you'd pull the 3x out, and then what would be your first term? It would be 1, and then minus 3x over here. So that when you multiply, you get what you started with, right? So that's exactly what we're doing here. Now, 1 minus cosine squared x. You're going to start training your brain to look forward a little bit. This side is all in terms of sine. So if I could figure out a way to convert cosine squared x to sine squared x, that would be fantastic. So where am I going to start? I'm going to look at my Pythagorean identities. And so you might go here to cosine squared x and see that you can write it as 1 minus sine squared x, which is fine. You'll still get the same answer. That's actually something that's really cool about these problems, is that the way you verify and the way that I verify these could be different and will both be correct as long as our steps are proper. So you could take a different route and we can get the same conclusion. Totally fine if that happens. It actually takes me a long time to grade these tests because of that fact, because everybody can do it a different way. So 1 minus cosine squared x, I'm actually going to use that whole term, that whole quantity of 1 minus cosine squared x. It says I can just write it as sine squared x. So sine of x. This whole piece right here is getting shifted to sine squared x, which gives me what? So again, I haven't worked the right side at all. I'm just working the left side. So I get sine cubed x equals sine cubed x. And I like to give these checks when I verified them. So I went back to the first one and did it even though you couldn't see it in the screen. So as you can see, these aren't terribly challenging. You just have to know these tricks to try, and thankfully, I mean, it's typed up right there on your notes for you. So normally this is a group challenge for my classes, so I have you guys try and figure out how to verify that identity, and you come up with many different ways, but because this is a video, I don't really have that opportunity, so we're going to do it together. We have tangent theta plus cotangent theta equals secant theta times cosecant theta. So in this particular video right here, in this particular problem, which side looks more complicated, the left side or the right side? It's kind of your preference. Because I have an addition sign here in tangent, which I can rewrite, and cotangent, I'm just choosing to work the left side. So how can I rewrite tangent? One trick is to put in terms of sine and cosine. So of course I have this memorized because I've been at this a lot longer than you have, but you're starting to see tangent's ratio is y over x, right? And sine goes with y and cosine goes with x, so it all makes sense. Cotangent is cosine theta all over sine theta equals secant theta cosecant theta. So now what are we going to do? Well, now we have two fractions, so we should try and get common denominators. So this one needs a sine theta and this one needs a sine theta. This actually makes me really happy because I'm going to end up with sine squared theta, which means I can use a Pythagorean identity of some sort or possibly use one. So you're going to start looking forward to seeing that combination. Oh look, cosine squared theta also, ding ding ding. So in my numerator, I'm going to have sine squared theta plus cosine squared theta all over cosine theta, sine theta. Which again, it doesn't matter that if it says cosine theta or sine theta, the order of that, because in math, when you're multiplying and adding, the order does not matter. So continue on with this problem. This needs to still be copied on every single step. I don't know if you guys have picked that up. This right here is 1 because sine squared theta plus cosine squared theta is 1. My favorite. So now I'm at this point where I have 1 over cosine theta times sine theta equals secant theta cosecant theta. And if you see this, this is exactly what we needed. 1 over cosine theta is secant theta, and 1 over sine theta is cosecant theta. So we get secant theta cosecant theta. Sometimes students have a hard time with this, so I just want to point this out for you. 1 over cosine theta times, not adding, but multiplying, times 1 over sine theta. These are equivalent statements right here. You can go from here to here, right? If I do 1 times 1, I get 1, and cosine theta times sine theta is that right there. So 1 over cosine theta is secant theta, and 1 over sine theta is cosecant theta. Okay, moving on. Next one. Woo, that just stepped it up a notch, but that's okay. We can handle these. So the first thing that we might want to try is switch to sines and cosines on the side that looks more complicated. So this side definitely looks more complicated, but it's already in terms of sines and cosines. Don't go switching it. If it's already in terms of sine and cosine, try something else in most cases. So the next thing it would be get common denominators. Okay, cool. It's a little messy, but this one needs a sine of x, and this one needs a sine of x. And after the last problem, you should be picking that up. And then this one needs a 1 plus cosine x, and this needs a 1 plus cosine x. Now be very careful when you multiply this out right here, because you will not be harming any animals. So make sure you follow the FOIL method. So in the numerator, we get sine squared x plus, and I'm going to FOIL this out now. 1 times 1 is 1, plus cosine x plus another cosine x. That makes 2 cosine x's plus cosine squared x all over sine of x times 1 plus cosine x. I'm leaving the bottom in factored form for now. We've learned in other problems that that can sometimes be helpful to only work in the numerator and not the denominator. So let's see what happens here. Now, if you notice this is sine squared x, positive sine squared x plus positive cosine squared x. Those two things together make 1. So that 1 is here, and then I have the 1 from here, plus 2 cosine x all over sine of x times 1 plus cosine of x equals 2 cosecant x. I'm actually going to put like a tricky on this, a tricky. It's not really that tricky, but it's got a lot of good skills in it. I really like this problem. So it takes you back to some algebra combined with that Pythagorean identity. It's great. 1 plus 1 is 2. So you may be working through this going, when the heck is this problem going to be done? It's close, but it might be hard for you to see at first. So the next piece to this problem right here is noticing, what do these two terms have in common? Oh, they're both divisible by 2. So if I pull out that 2, what do you notice? We have some common factors in the numerator and the denominator. Sweet. So these will cancel, and I have 2 over the sine of x. So 2 over the sine of x is just cosecant x. So 1 over the sine of x is just cosecant x. So I get 2 cosecant x equals 2 cosecant x. Check. I want to show you guys this little piece right here. This is 2 times 1 over the sine of x is another way to write that. So the reason why I'm showing you that is so that you can see the 2 times, this can be written as cosecant x. But it's something that you can do in your head, so that's why I have it here and not written as a separate step. If you need the additional step, take the additional step. Ain't no shame in that game. I'm on fire. Alrighty, flip it over. Last problem. There are many ways to approach this problem. You can switch to sines and cosines. You can do a bunch of different things. What I am going to do for you in this problem is show how to multiply by the conjugate. So that doesn't mean that you have to multiply by the conjugate in this problem, but I'm just showing you that tool. So what we're going to do first is which one of these would actually have a conjugate, this fraction right here, and which side actually looks more complicated, this one here. So I have cosine t over sine t plus, and this is where I'm going to multiply by the conjugate. So I get 1 minus cosine t and 1 minus cosine t. What's really nice about multiplying by the conjugate here is that I'm going to produce something that's squared, which means that I can probably use Pythagorean identity. But let's see how this works out. So in the numerator, I'm going to go ahead and FOIL. And in the denominator, because this is a conjugate, it follows the difference of squares pattern. So it's 1 minus cosine squared t. If you don't understand that, then just go ahead and FOIL it out. You'll see that that's what it equals. If you don't know the shortcut, A-okay, you can still get it. So this is supposed to simplify to cosecant t. So here we are now. What can we do? Because this denominator is in terms of sine, you can try and get common denominators, but 1 minus cosine squared, grab your identity sheet. Because it's squared, you're looking for another way to write it. It can be written as sine squared x, which will save us some time because that's much easier to get common denominators with when it's written as sine squared, because this is already sine, than it is when it's 1 minus cosine squared t. Okay, moving on from there, we're going to go sine t times sine t, and then we get cosine t, sine t. In the numerator, we will have plus sine t minus sine t cosine t all over sine squared t, because we got that common denominator. So from here, you can see these terms right here are going to cancel out. They just cancel out. The positive one is canceling out with the negative one. So then you have sine t over sine squared t, which equals cosecant t. And then from there, this sine t will reduce with one of those. So it's 1 over the sine of t equals cosecant t. And we know this is cosecant t equals cosecant t. Check. Just pointing this out on this part right here, remember this is sine t over that sine squared t is sine t times sine t. So that's why I can cancel it out and get the placeholder of 1 there. So that is it for 5.1a. You're going to go home, do your homework, and if you need help, you're going to go on to Professor Rob Bob's website, YouTube channel, or find somebody else's and look at those. But mainly it's all stemming from this identity sheet. And if you can't get a couple of them, then I would definitely call someone or Skype with someone and try and get some help. Alrighty, have a great night.